There is always a need to validate the stability of your machine learning model. You can't just feed the model to your training data and hope it accurately works for the real data it has never seen before. You need some kind of assurance that your model has got most of the patterns from the data correct and it's not picking up too much on the noise. Or in other words, it's low on bias and variance. There are many ways to prepare your dataset before fit it to the model. Let's start with holdout method. The basic idea of this method is to remove a part of the training data and use it to get predictions from the model trained on the rest of the data. The error estimation then tells us how our model is doing on unseen data. This is a simple kind of cross-validation technique, also known as holdout method. Although this method doesn't take any overhead to compute, and it's better than the traditional validation, but it still suffers from issues of high variance. This is because it's not certain which data point will end up in the validation set, and the result might be entirely different for different sets. We have been using this method from the beginning of our course. Now let's load the breast cancer dataset. After that, we split our dataset to train and test, giving the test size 20% and the train size 80%. After that, we will classify our data using KNN classifier. We notice that F1 score is 89%. Now let's see how we can improve this score using k-fold cross-validation. As there is never enough data to train your model, removing a part of it for validation might make a problem of underfitting, because by reducing the training data, we risk losing important patterns in our dataset, which in turn increases error indicated by bias. In k-fold cross-validation, the data is divided into k subsets. Now the holdout method is repeated k times, such that each time one of the k subsets is used as the test set, and the other k-1 subsets are put together to form a training set. The error estimating is averaged over all the k trials to get total effectiveness of our model. As can be seen, every data point gets to be in a set test exactly once, and gets to be in a training set k-1 times. The big advantage that comes with k-fold cross-validation is that it's much less prone to select bias, since training and testing is performed on several different parts. In particular, if we increase the value of k, we can be more sure of the robustness of our model, since we have trained and tested on so many different sub-datasets. The only possible drawback of this method is that as we gain robustness by increasing k, we also have to train more model, which is an expensive process. As general rule, we can set k to 5 or 9, but nothing is fixed and it can take any value. Now let's see the F1 score after using cross-validation and splitting our dataset into 5 folds. The F1 score now is 94.4%, which is much better than the F1 score of holdout method. The last cross-validation method we are going to talk about is repeated random subsampling. Repeated random subsampling is perhaps the most robust of cross-validation methods. Simple to k-fold, we set a value for k which signifies the number of times we will train our model. However, in this case, k will not represent the number of equal size partitions. Instead, on each training iteration, we randomly select points to be for the testing set. The number of points we select will be a certain percentage we set for the testing set. For example, if we selected 15%, then on each training iteration, we will randomly select 15 of the points in our dataset to be set aside for training. The rest of the procedure continues the same way as k-fold, training on the train set and testing each model on its unique test set, and finally, average out the results at the end to obtain a final accuracy. The clear advantage of this method is that the population of train test split is not depending on the number of iterations. We can even set different percentages for the test set on each iteration. The randomness may also be more robust to select bias. The disadvantage of this method is that some points may never be selected to be in the test set. At the same time, some points may be selected multiple times. In this example, we will split our dataset into 5 folds and repeat it 2 times. We will classify each fold using KNN and compute the average F1 score of the 10 sub-datasets. We see now that we have a minor improvement over K-fold cross-validation by getting F1 score of 94.7%, which is very good, because the higher the score, the harder it gets to make an improvement on it. So anything you do to improve your model score, even a little bit, is great. In the next lecture, we will learn how to analyze learning curves to detect how good our model is doing and if you have overfitting or underfitting situation. See you then.